So I'm going to talk about fresh mathematical theory, which so far has not been compared to experiment, unlike the previous talk, which was based on the previous theory. Hold on, let me. Oh, okay. So I'm going to talk about some solution of the loop equations, and I have to explain to you first the general situation. These are equations which are very well known in gauge theories, where they describe fluctuating vector field like gluon field or electromagnetic field. And in '93, I applied the same technique, loop equations, for the turbulence. But I couldn't solve these loop equations and couldn't find any predictions except only one, which was area law. It was predicted in '93. It was a consequence of the approximate solution of the loop equations in the limit of large loop. And that is what Kartik was talking about. That 30-year-old prediction was finally verified by work of Kartik and Srinivasan and others. And then Kartik further investigated various other scaling properties. So we know that these loop equations, which were used for the prediction of the area law, they work. But what was verified so far was just the WKB limit, quasi-classical limit of the loop equation. Today I'm going to talk about something rather shocking, which is exact solution of loop equations. They can be solved exactly, and the solution is rather complex, so I cannot yet compare it with experiment, but I am going to present it to you here. So let me first remind you what we are trying to solve. This is Navier-Stokes equation, and it looks deceptively simple. Here is an equation, time derivative velocity equals, that's how I prefer to write the loop equation, using everything in terms of vorticity. And that is gradient of enthalpy, which will drop in loop equation. So we have to solve this set of equations and see what happens when viscosity goes to 0, but you fix the energy dissipation. Turns out that energy dissipation is proportional to viscosity times entropy. So when viscosity goes to 0, the phenomenon of turbulence means there is anomalous dissipation. Entropy increases in some regions where there is large vorticity, and that's what Kartik described, this behavior of entropy. So it fluctuates and becomes very large, and that's how you get anomalous dissipation. So that's the essence of the turbulence. We want to see how it happens. We want to understand the physics behind it. So naively, in the limit of zero viscosity, Navier-Stokes equation tend to Euler equations. You could just drop the first term, and you will get Euler equation. But there are regions of large vorticity where this gradient compensates small factor of viscosity. This phenomenon is well known in boundary layers. Exactly that happens, but not just boundary layers. There are vortex sheets and singular vortex lines. So there are regions of high vorticity. So what happens is that these regions okay. So these regions are randomly. How would happen that it is not visible? Let me see. Anyway, these regions are randomly distributed in space, making velocity and vorticity stochastic variables. So at any given point, with some probability, this point will be that point of singular vorticity. So at any given point, local vorticity has a probability distribution because of these randomly moving singular areas. So at any given point, vorticity is intermittent and in average could be large. The fluctuations are large. Now this approach, there is approach outlined by Hopf, and that approach was used just for kind of wishes and prayers. It was never used to solve anything, but he still wrote some equation which is called Hopf equation, and he introduced the functional, which is exponential of integral of some source j times velocity field, and then he observed very important thing that yes, this functional will satisfy some linear functional equation. Time derivative of this functional, you should differentiate velocity inside in this exponential, and you'll bring down Navier-Stokes equation, and you will get something like that. You could take anything you get after time derivative of velocity, like all these terms, they related to velocity, and velocity can be replaced by functional derivative with respect to source, and you get what is called Hopf equation. You get some operator depending on source and functional derivative of source. So it's easier to write than to solve. Nobody ever solved Hopf equation, and it was considered like something symbolic to hang on the wall and pray. Huh?
Viscosity is zero or not?
What?
Number 4, equation number 4. Is viscosity zero or not?
Viscosity, I didn't say viscosity is zero. Did I?
No, you can. I'm asking.
I didn't. No, it's Navier-Stokes with viscosity satisfy. This term is proportional to, yeah, no problem. No, this of course can be written for arbitrary viscosity. It doesn't matter whether viscosity is zero or not, and then you indeed want to tend viscosity to zero and see what happens. But with zero viscosity or finite viscosity, you still cannot solve functional equations. Functional equations are not born to be solved. They are born to be symbolically described and studied. But what I'm going to tell you today is that there is, how do I move it? Huh? You know what? Okay, I think it's fine. Well, first of all, what are we going to solve? I think I know what happened. I think I know what happened. I think yes, I think I can change the scale and it will be then visible. Yes. Okay, I'll have to show it like that. So the turbulence corresponds to the degenerate fixed point of the Navier-Stokes dynamics. By this I mean the following. We find the evolution of the velocity field following Navier-Stokes dynamics, and then it starts covering certain manifold. We don't know what manifold, but it's covering that manifold, and that leads to probability distribution for velocity field. In case of Newton mechanics, which would be without viscosity, we know that manifold. That's energy surface. It's a ergodic hypothesis. The velocity evolution of the conservative system covers energy surface, and we know solution of the Hopf equation from that point of view. You have a degenerate fixed point. Any point on the energy surface is a solution, and you approach that solution depending on initial data. So eventually you cover the whole energy surface. So the question is, what is analog of that in case of turbulence? It's not energy surface because it's dissipating. So the decaying turbulence is a degenerate fixed trajectory. So if we don't add sources, random forces which compensate for loss of energy, energy will dissipate. So you will have what I call fixed trajectory. So it will be some universal trajectory which goes to zero. Velocity goes to zero, however, the shape of the distribution is the same along this trajectory. It's we're going to discuss it in a moment. But there is some universality, but not complete universality. Fixed point means some universal manifold covered with some measure. And fixed trajectory is time-dependent manifold covered with some trivially scalable measure depending on time. I'm sorry, if you are speaking without microphone, I can't hear it.
The non-changing shape of the distribution is an assumption.
I will describe that in a
But it's
moment.
an assumption or not?
Huh?
It's an assumption. Is it an assumption? It's a
Yes.
hypothesis. It's an assumption.
Okay. So I will answer many questions later because you're asking questions which I thought about, and I'm going to answer them. So the Hopf equation for the Navier-Stokes dynamics is compatible with such trajectory, but the Hopf equation is too general and too complex to compute anything. Its complexity of the Hopf equation is equivalent to non-Gaussian functional integral, something which Professor Glim was talking about, analogous to quantum field theory, and that misplaces turbulence in the same category as critical phenomena in statistical physics. It is much simpler in our theory. So what my claim is that turbulence is less than a field theory, not a field theory. It is something much simpler, exact solution. But not the turbulence with Gaussian random forces, but the decaying turbulence. That is a simple system. That's what I'm saying. So the loop average, which I'm going to study, is a particular case of Hopf functional, where the source is concentrated in a fixed loop space. So consider a source which is integral over the loop of three-dimensional delta function. If you substitute such source in three-dimensional integral over space, the three-dimensional integral will go away, and you will get just one-dimensional integral around the loop. So to get a loop functional, which is exponential of circulation, you need to consider singular source in Hopf functional, which is sitting on a loop, fixed loop in space. So if you take such source, and then you will get this exponential. Now, note that there is this imaginary unit here. It is important. The thing is that this loop average is only defined for imaginary factor here. Why? Because its distribution is exponential. There are very, very long tails. Distribution of circulation, which was described by Kartik, is not Gaussian. It's exponential. So if I have here a real factor, it will not converge. Only phase factor of circulation, exponential of I times circulation times some number, exists. So Fourier, effective Fourier transform exists, but not Laplace. So there should be imaginary factor here. And then such thing mathematically exists and can be studied. So now I'm talking about loop equation. So in 93, we derived the following equation for this loop average. So time derivative times viscosity equals some, this is kind of obvious thing. I just differentiated velocity in exponential and used Navier-Stokes equation, except I dropped the term with the gradient because integral of gradient over the closed loop equals 0. So you'll get something very simple. It's called theorem, like Helmholtz theorem for time derivative of circulation. In time derivative of circulation, the gradient of enthalpy or gradient of pressure drops. So you'll get a very simple term. But my observation was that it is even simpler than that. All these terms can be written as some operator with functional derivative with respect to loop. So both of these terms, curl of vorticity and velocity cross vorticity, they both can be written as some operator which depends on functional derivative. So that now looks like Schrödinger equation. Time derivative of psi function equals some Hamiltonian applied to psi function. So again, the same symbolic mess. Who can solve functional differential equation? Well, that's what I'm going to do now. This equation, unlike Hopf equation, is solvable. Why? Because this operator only depends on functional derivative. It does not depend explicitly on the loop. If the Hamiltonian depends on the gradient That is a situation when momentum is conserved. So a plane wave will be solution of the loop equation. In this case, it's going to be a plane wave in loop space. In other words, what happens is that since this operator doesn't depend explicitly on the shape of the loop, but only depends on functional derivative, I can immediately write the solution. And then it took me 30 years to understand the meaning of this solution, because I couldn't believe myself 30 years ago. So the solution has the following form. Solution is exponential of integral of some unknown function p over the loop. So this function p does not depend on coordinate. It only depends on theta, which is the parameterization of the loop. So this exponential, this factoring exponential is linear functional of the loop. So it only has the loop here, and p does not depend on the loop. And if you have such functional, then functional derivative acting on this psi function will just bring down time derivative of p, because everybody knows since quantum mechanics that that gradient of exponential equals p, momentum. In this case, it is momentum in loop space. But still, if you apply functional derivative to this exponential, then any functional derivative will become ordinary number, not an operator. You immediately get equation for p. You see that if you found such p, that its time derivative is this operator with functional derivative replaced by p, if you solve this equation, which is no longer a functional equation, it is actual ordinary differential equation for a function of time and one variable theta. So if you solve this equation, you solved Hopf equation for the Navier-Stokes without any approximation. Of course, it's not the most general solution, it's a fixed trajectory solution. But this turns out the good news is that there is a solution with very reasonable physical properties. That's what I'm going to describe. First of all, it took a lot of effort in mathematics, which I'm going to skip, to actually compute explicit form of this operator. So this operator involves, don't think it is Laplacian. Delta p is discontinuity. So this operator is rather a simple algebraic function, but it involves discontinuity of vector p. Why discontinuity? For the following reason. What is gradient? What is gradient? You have to move one point on the loop, aside of the loop. That means you take functional derivative and integrate that functional derivative on a very small interval. Then you move a little piece of the loop. If you take functional derivative with respect to loop and integrate it over all very small interval of the loop, plus minus 0. But that functional derivative with respect to loop gives p prime. So integral of p prime from minus 0 to 0 is delta p. So you get discontinuity because varying with respect to c, you get p prime, and then you have to integrate this p prime over a very small interval, and that's how you get discontinuity. And that's exact statement. You don't have approximation here. So this is exact parametric invariant, time-dependent equation for this unknown function p. So if you solve this equation, if you found p which solves this equation, then this psi will satisfy the loop equation, which is Hopf equation, and that means you found some viable generating function for the probability distribution in decaying turbulence. So let's solve it and see what happens. So back in the 90s, when I derived that equation, it looked so scary that, first of all, nobody could understand what I'm talking about, and second of all, I myself didn't understand what I was talking about. So I shelved it, and instead of trying to solve it exactly, I came back to the loop equation and found out what was WKB solution. This Schrödinger equation can be solved in approximation which is called WKB. And that gave me area law, and that other law which KITP describes. So area law corresponds to solving this loop equation as a Schrödinger equation in the WKB approximation, where it simplifies. Now I'm trying to solve it exactly. So here is an analytic solution, which I found a few months ago. So first of all, this function p of t has trivial dependence on time, 1 over square root. Why? That's actually very easy to see why, because you have equation here where time derivative of p equals some homogeneous functional of the third degree. So the right side scales as p cubed. So if p has a factor of t to some power, then this right side have that factor to the third power. So you could, if you have the homogeneous equation, regardless linear or it is singular, but with respect to amplitude of p, it is cubic. The right side is cubic with respect to p. Cubic, and this one is square times first cubic. The whole right side is cubic with respect to p, homogeneous functional of the third degree. And then, therefore, this is exact solution has this, its fixed trajectory. It's 1 over square root of t plus t naught. And eventually, I will tell you later, it corresponds to energy decay is 1 over t, which is not far from experiment, but I'm not yet ready to discuss experiment. So this function f of theta doesn't depend on time, and there is a fixed point equation for this function f, and I found solution of this equation. And whoever wants to check it, he has to go into my paper. I have a reference to the Mathematica book, and there is a Mathematica code which substitutes this step by step and checks that indeed it solves the equation. So this omega here is just random arbitrary rotation matrix. It's a very degenerate solution, by the way, which is what we wanted. It has arbitrary rotation matrix, which I take as random element of rotation group. And then it has some parameters beta and alpha k. And when you substitute that ansatz into equation, you'll see what are relations between these parameters. So I'm here approximating function of theta by its value on the equal angle. So I'm approximating the curve, which is a fractal curve, as a polygon. And then, of course, I will have to extend number of vertices to infinity. So this function p of theta has discontinuity at every theta. So I find it as a limit of a polygon, which has some large number of discontinuities. So I solve solution with discrete version, and then tend n to infinity. So limit of this to n when n goes to infinity will solve the original equation. And if you substitute, you'll find out that there are at every fk are vertices of this polygon, and they involve some function alpha k, and alpha k is such that the difference alpha k plus 1 minus alpha k is some plus minus some like Ising variable, plus minus 1 times beta. And beta must be a rational number. And it must be a rational number for the periodicity. It has to be periodic curve. So only if beta is rational of a rational fraction of 2 pi, this curve will close. It will be periodic. So that is not made up model. It looks like made up model. You would kind of cook such a model and say, okay, it looks like turbulence, let's study it and see how it measures experiment. No, I cannot change anything in that model. All these parameters here come from the loop equations. If I substitute and change any of these relations, say that beta is not rational or sigma squared is not 1, it will not solve equation. So it's a funny situation. The statistical model, because this is statistical model, some random variables, statistical model actually solves fixed point equations for turbulence. From the physics, for the physicists, for a theoretical physicist, it's called duality. You find different system, dual system, which describes the fractal curve in complex space. And that dual system reproduces the correlation function of original system. So I cannot, my solution doesn't tell you what is velocity field. It's not solution for velocity field. It's a solution for the Wilson loop. In other words, I can compute correlation functions of velocity, of vorticity rather, but I cannot say what is vorticity. I can only compute Wilson loop and its functional derivatives, which means I could compute correlation functions of vorticity. So this system have the same information as the loop function, because it gives answer for the I'm computing loop average as a function of the loop. Loop is arbitrary here. I could find variations, and it is complete solution. However, I don't have complete formulas for velocity field, because longitudinal component of velocity field drops here when only vorticity is left. So I can compute correlation functions of vorticity.
What are physical units of this P?
Huh?
What are physical units of this P have?
Physical units, F is dimensionless.
What P?
Huh?
Of P?
P?
Of your solution, what are physical units?
Physical units, P has the same dimension as velocity. So square root of viscosity by time is just what is needed.
So you have characteristic velocity scale.
Hmm?
So you have it means that there is a characteristic velocity scale, right?
Yes.
And it's come from experiment?
Let me go slightly further. I will answer that question. So here is what happens. I can now compute various observables. For example, so this is solution, and I could study solution. It is like one-dimensional Ising model, and I could make exact computations for arbitrary n, and then tend n to infinity. I call this system Euler ensemble. So the simplest thing is partition function. Just sum over all different configurations, just number of states, just sum of unity over all different configurations, partition function. And once you do that, you'll find remarkable thing. You'll find relation with thing called Euler-Toschians, because a part of my solution is fractions of 2 pi. My beta, my parameter, which periodicity required that this beta is a rational function. Now, rational numbers were enumerated by Euler, I don't know, 300 years ago. And they are enumerated by a thing called Euler-Toschians, because like 2/3 and 4/6 is the same number. So the number of fractions with given denominator is given by the number of the relatively prime, mutually prime numbers p and q, where p less than q, and that's called Euler-Toschian. And Euler derived beautiful formula for Euler-Toschian, expressing it in terms of prime numbers. So this is a very well-defined object in number theory, and I computed it and find asymptotical behavior of this thing when this parameter which I introduced here, the chemical potential, mu goes to 0. And then you could compute entropy. And now here is the most important fact. It is not a solution of turbulence if I don't get anomalous dissipation. So my entropy should diverge. So I compute this entropy. It's exactly calculable. And here is the result. The time derivative of energy, which is viscosity times entropy is square of vorticity, is some universal number times viscosity divided by my factor of mu squared and 1 over t squared. And this is what I computed. So I have the model is solvable, I can compute it, and indeed I find that viscosity is enhanced. in my solution, viscosity is divided by mu squared. So mu goes to 0. So this is anomalous dissipation. So, okay, I'm almost done. Then I don't answer any questions in that minute. So then I computed higher moments, and they are related to these horrible expressions with Bernoulli numbers, gamma functions, zeta function, but anyway, they're calculable. And the simulation, the numerical simulation of my system is very easy because it's less than one-dimensional. It's what's called Markov chain. If you have some number of sigmas on the circle, and probability for each sigma only depends on the previous one, that system is called Markov chain. And that is, you don't have to remember all sigmas. You just randomly walk along the circle, and all you need to do is count number of positive and negative sigmas, and every step along the curve will just change either n plus or n minus. If you have sigma equal 1, then you diminish a remaining number of n plus, etc. for n minus. Well, of course, here it is n minus, I'm sorry, typo. So because of this Markov property, it doesn't take memory. Simulation of the system takes O of n to the 0 memory. So we simulated it with my collaborator Max Bulatov for n equal 100 million, and we took 1 billion samples, and we could take more. It's just how many digits could double numbers hold. And that is large enough to diminish statistical errors. So we get very, very precise results. I'm not going to report them today because I don't have time, but we get something which is as good as exact solution, but also I have these exact solutions for certain things. Now, the most interesting thing, and I would steal 1 more minute of the lunch.
Yeah.
We're running late. I don't know if you started late. Did you start?
No,
Did you start late, Sasha?
Yes.
It's overtime. So.
If I need 5, because that's my last slide.
Thank you. And then we'll just not take questions.
Yeah. So that's my last slide, and it's very important. When you are studying fixed point or fixed trajectory, in my case, you might want to see what happens, how you approach that. It's called Lyapunov stability. And if that would be a fixed point, then approach would be exponential. You would perturb solution near a fixed point, and then you will find a linear equation for the deviation from fixed point, and Lyapunov exponent will give you exponential approach. But in my case, it is fixed trajectory. And that fixed trajectory depends on time in a very specific way. Turns out, oh miracle, the deviation from my fixed trajectory has not exponential, but power-like spectrum. I got scale invariance and multifractal for free without having any conformal symmetry, without any field theory. This is exact statement. My small deviation from my solution, if you substitute in the equation will be such that solutions exactly are power-like, and the power spectrum is determined by very specific algebraic equation, which of course is more and more complicated the larger n, but at any finite n you could compute it, and then of course you need to use Markov chain to approximate, go to infinity. So the nice thing is that, again, it's easier than conformal field theory. It's easier than theory of critical phenomena, because in theory of critical phenomena, nobody can compute spectrum of anomalous dimensions. Here I have an equation. Okay, so our solution shows non-perturbative effects, which are missing in weak, its conclusion, in weak turbulence, which is expansion in inverse powers of viscosity, whatever some people say. I know that my perturbation theory, if you perturb in the linear term in Navier-Stokes, you will get expansion in inverse powers of viscosity, which is expansion in terms of Reynolds number. So it diverges when you go to turbulence. So The most shocking thing is the quantization of parameters. I told you that this loop equation is equivalent to Schrödinger equation, so I get quantum effects, quantization, which you would never see in perturbation theory. And they follow from this mathematical equivalence. And then also, it's remarkably simple because it's algebraic. It's not a field theory, it's a Markov chain. So what we need is real and numerical experiments with decaying turbulence at extreme Reynolds number to verify predictions of this theory. So the theory exists. It can be investigated using methods of number theory, and it has not yet been compared with experiment.
Thank you, Sasha. We're going to go ahead and break for lunch. So for those of you who have questions for Sasha, grab him at lunch.